Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Hello everyone, welcome to this lecture again. Let us continue our discussion on the tensile test, and we are looking at the results of a typical tensile test, and then we are looking at basically the interpretation of the results, which is a basic outcome of a simple tensile test. So in the last class, we have looked at the engineering stress strain curve and various parameters one can derive from that outcome of the results. So we also looked at some derived parameters like true stress, true strain curve, and what is the usefulness of this curve and how it is related to engineering stress strain parameters. So we will continue our discussion on that, and what we are going to discuss today is how this slip character and the strain hardening coefficients for several metals are compared. When you compare these parameters, how do they appear? So for example, if you look at this table where the stacking fault energy and strain hardening coefficient and slip characters, they are all summarized for typically for stainless steel, copper and aluminum. What you have to notice here is the parameter stacking fault energy. We have already seen this. This is not new to us. We have a sufficient background to understand this. What is stacking fault energy, which is expressed in million joules per meter square. Okay. So the stacking fault energy plays an important role in the determining the deformation characteristics of polycrystalline material. This is a fundamental property or characteristic of each material. Okay, so if you take the stacking fault energy, by just looking at the values, you will be able to predict some kind of dislocation activity, right? So the stainless steel typically, which is having the stacking fault energy less than 10 millijoules per meter square, has got a strain hardening coefficient of 0.45. Okay, and then the slip character is named as planar. So we will try to see what it is. Okay, then if you go to the next metal, copper, which is having a significantly higher stacking fault energy, has got the strain hardening coefficient of 0.3, and the slip character is described as planar / wavy. Finally, for aluminium, the stacking fault energy is very, very high, around 250 millijoules per meter square. For that, the strain hardening coefficient is 0.15, and the slip characteristic is designated as wavy. So now we have to just look at the individual, deformation characteristics of each of these metals. So the table basically summarizes the material having two extreme cases of stacking fault energy. Of course, the copper is having some middle range. So how this is going to determine the deformation characteristic of these materials. So now we can relate these things with the strain hardening coefficient. So what is the strain hardening coefficient tells us from the previous discussion? What do we understand? The more the strain hardening value, right, that means it will the material will have a huge ability to strain harden. Strain hardening ability will be very, very high. I mean, that is the index of strain hardening coefficient, right? So the material which is having a very small stacking fault energy, you can see that the strain hardening coefficient value is higher. So we have a very nice trend here. Lowest stacking fault energy, highest strain hardening coefficient. Highest stacking fault energy, lowest strain hardening coefficient. And these two are characterized as two extreme slip character. One is planar, other is wavy. We can relate all of them. Very interesting table and very important table as well. So if the material having very low stacking fault energy, it is going to strain harden significantly, but the slip characteristic is planar. That means the dislocations will try to move only in a planar fashion, not in the three-dimensional movement. It is not going to climb or cross slip so easily. They are all going to just pile up. The glide will be, they are going to glide only a single plane, and that is going to be a primary deformation mode. That's all we have to look at it. For a copper which is having the middle range of stacking fault energy, which will strain harden, but not to the extent of stainless steel, but at the same time it will be better than the aluminium. It is going to strain harden. So obviously it is going to have, or it is going to display both the slip characters, namely planar and wavy. So this is something very important you have to keep in mind. And if you look at the aluminium, which is having a very high stacking fault energy, and then you can relate all these stacking fault energy values with the dislocation dynamics and mechanics, which we are already familiar with, right? But when the stacking fault energy is very high, in this context where we are talking about mechanical testing, especially a tensile test, the material is having the low strain hardening coefficient is not going to strain harden much as compared to the stainless steel or copper. And the slip character is going to be wavy. So what is wavy slip? Wavy slip means it is going to, the dislocation mobility will be in 3 dimension. I mean, the 3-dimensional mobility is facilitated by the high stacking fault energy. You can just quickly move up and down. You can easily cross slip and climb and all that. But it may not be very, climb and all, it is primarily in high temperature mechanisms. But here we are talking about cross slip, easy cross slip, and then it can move onto a different slip planes, which is available at a different height. So that's all we are saying. So when the deformation takes place with such an ease, so the substructure which is going to form is they are all going to appear as a wavy in nature. That's why it's called wavy slip nature. Okay. So all the dislocation walls, bundles, dislocation cells, substructures, all of them will appear in a wavy form. That means it's not an organized form. On the other hand, the same dislocation substructures will appear in a planar fashion. So it will not be like a random waviness will not be there. So it will be all planar segments. Okay. So that is by just looking at the dislocation substructures, you will be able to characterize the deformation behavior. In a first look itself, you can just understand this, and then of course, depending upon the interest, you can go to any level of analysis and investigation. So the strain hardening coefficients which you obtain from a simple tensile test tells quite a bit of deformation characteristics if you connect that with the stacking fault energy. That's the message I want to bring here. The direct connection between the strain hardening and dislocation mobility makes it possible to relate strain hardening coefficients with stacking fault energy values as shown in the table. So when the stacking fault energy is low, the cross slip is restricted. So the barriers to dislocation moment remain effective to higher stress levels than in the material of higher stacking fault energy. That is to say, the low stacking fault energy material strain hardens to a greater extent. Note that the strain hardening coefficient increases with decreasing stacking fault energy, while the slip character changes from wavy to planar mode. Okay, so that is one aspect of the tensile test, the another important aspect is instability extension. So normally we look at in a tensile test, the specimen is subjected to necking beyond certain load, right? So that is called instability intention. So let us learn a little more on this. Necking or localized deformation begins at maximum load, where the increase in stress due to decrease in cross-sectional area of the specimen becomes greater than the increase in the load carrying ability of the metal due to strain hardening. Okay. So the moment the cross-section of the specimen becomes smaller, and it becomes a problem there, because the load carrying ability of material is affected. That is what you have to see. Okay. So that is what the strain hardening coefficient also will indicate. This condition of instability leading to localized deformation is defined by the condition dP is equal to 0. Okay, the change in load at the maximum, that is dP is equal to 0. So we can just relate this, use this condition of instability using this relation. We will be able to derive few more equations. P is equal to sigma A and dP is equal to sigma dA plus A d sigma is equal to 0. And from the volume constancy relationship, we can write it like this: dl by L is equal to minus dA by A, which is equal to d epsilon. And from this instability condition, if you apply this instability condition here, dP is equal to 0, then minus dA by A is equal to d sigma by sigma. So that at a point of tensile instability, we reach an equation d sigma by d epsilon is equal to sigma. This is very, very useful and very important relation. Now we can look at all this in a graphical way. So how to find the point of necking at the maximum load? There are two ways. Okay. So the one is, this is the sigma versus epsilon plot, where you look at the point and then draw a subtangent of unity. Subtangent of unity. Draw from the maximum load, draw a subtangent of unity. That will indicate the maximum load of necking, the point at which it's going to neck. Or the other way to find out is, find out the intersection where the d sigma by d epsilon is equal to sigma. So that is what we have found here. Okay. So either this or this, both of them will find out the point of necking at maximum load. Okay. So this is very important, right? And you can also check in your simple tensile test. You can plot these two things, work hardening rate versus strain and stress versus strain plot. You will be able to see that the maximum UTS will be the lowest value of d sigma by epsilon will be matching this. So you will see that. So another interesting way of analyzing this necking phenomenon is, let us go through that. The necking criterion can be expressed more explicitly if engineering strain is used. D sigma by d epsilon can be written like this, where d sigma by dE into dE by d epsilon. So engineering strain, we know that we can express in terms of dl by L naught, and again the true strain is dl by L. So we can manipulate this. Sorry, d sigma is dl by L naught and dE is dl by L. and this can be written like that, L by L naught, and this becomes L by L naught becomes 1 by 1 plus E, d sigma by dE times 1 plus E, which is nothing but sigma. Okay, so we can rewrite this, d sigma by dE is equal to sigma by 1 by E. So what is the usefulness of this? This equation permits an interesting geometrical construction called Considère construction for the determination of the point of maximum load. Here again we are going to do the same exercise like what we have seen in the previous slide. Here it is called Considère construction or Considère condition, we can say that. So what you have to see here is this is a sigma versus epsilon plot. So you try to you first take a negative axis point A up to the unity -1, and from there you try to draw a tangent to this curve, and that point C, okay, that will give you the point of necking at maximum load. That is what this equation says. So if you simply look at this slope, that is d sigma by dE, which is nothing but sigma here plus 1 plus E. That's what's shown here. So the slope is sigma divided by 1 plus E. So this is what is shown here. So this stress strain curve is plotted in terms of the true stress against conventional linear strain. This is a kind of relation between the true stress versus conventional strain. Okay, that is also the way of looking at this. So this is what the description is given here. Let point A represent a negative strain of 1. A line drawn from the point A, which is tangent to the stress strain curve, will establish a point of maximum load according to this equation. Okay, so another important relation we can get it. We can obtain a simple relationship for a strain at which necking occurs. This strain is true uniform strain. If you recall, I just mentioned in the previous lecture that we just looked at discussing the strain hardening experiments, then expression something close to this, d sigma by dE is equal to n times sigma by epsilon. That expression we have seen. So if you recall that expression and then compare these two expressions, this equation and that expression, then you can relate this epsilon u is equal to n. That means the uniform strain up to the maximum load, which is equal to n. This is also very important relation. So what is that usefulness of the strain hardening coefficient? Strain hardening coefficient can also be looked at. It is equivalent to uniform strain. So the uniform strain is very important in the case of materials which is being subjected to metal forming operations, right? So the measure of ductility and formability and all, some idea it gives. So these relations are very important and useful in that context. Okay. So one final description about this instability in tension, which is also related to the different relationship we are looking at it. The true fracture strength is the true stress at fracture. So beyond the yielding point, beyond the maximum load, we just mentioned in the previous lectures that all these relationships are not going to be effective. So after the maximum load, what all we can derive, and combining these two strains, that is the intention of this slide. Okay. So we are talking about the true fracture strength. That means the true stress at fracture. So sigma F is equal to PF by AF, where the final cross-sectional area following fracture AF is determined from the measurement of averaged minimum diameter of failed halves of the specimen put together. Similarly, the fracture ductility is a true strain at the final fracture. So this also can be measured, and then we will see what we can do with this expression. So the reduction in area can be written like this: 1 minus e to the power minus epsilon f. And at fracture, we can simply substitute this values. I mean, this is a simple Coulomb type of equation where we are now looking at only at the fracture. Okay. So if you, it is not sigma, it is sigma f. It is not k, it is k1 and epsilon f to the power n. Or you can write an expression for k like this and then substitute this into the plastic strain. Epsilon p is k divided, sigma divided by k1 to the power 1 by n. And then this can be rewritten like this. We simply substitute this value of k1 here. So then you will get finally epsilon p is equal to epsilon f times sigma by sigma f to the power 1 by n. So we can now write, bring the another relation. This is engineering strain, which is equal to sigma by E. The total strain we can bring in. So we now know that epsilon P and epsilon E. So total strain is equal to epsilon E plus epsilon P, which is nothing but this expression, sigma by E plus sigma by K1 to the power 1 by n, which is nothing but sigma by E plus epsilon F times sigma divided by sigma F to the power 1 by n. So this kind of just a small manipulation gives us to visualize how to express the total strain in the tensile test results. So some useful relations you can relate. One final description about this instability in tension. What you are seeing in this schematic is this is a typical dog bone tensile specimen which is subjected to the tensile force here. The strain is less than epsilon EU. So the capital EU is the maximum load, engineering strain, that is called E is engineering and U is the ultimate. Okay, so this notation is given in this reference, so I have not changed that reference, but it is nothing but the strain at the engineering strain at the maximum load. So that is what you have to look at it. So when this strain is less than that maximum load, nothing happens, and then as the deformation proceeds, what happens? There is no necking here. So what is the physics we are trying to explain here? We'll see. During tensile deformation, strain is periodically localized at weak links. So when you say weak links here, it means the diameter in the gauge length is much smaller as compared to the shoulder portion. So that's what we are saying that. And for strains less than epsilon EU, that means the maximum strain, that is the strain at the maximum load. If it is less than maximum load, the work hardening in these areas strengthen the material enough relative to the material outside of them so that the instability is removed. So basically, when this is this cross section is being pulled in tension, immediately the necking doesn't form. The necking forms at much later stage. So what happens during that time, before necking, after deformation, plastic deformation commences? So in between these two times, what is the physics? That's what we are trying to see. So that means what happens? So the rest of the whole area is getting strengthened. So that is why it is almost like, it is equalizing the whole specimen through the uniform strain or something like that. Then the work hardening rate decreases with strain at the maximum load, the strain at the maximum load. The fractional decrease in the cross-sectional area at a weak link exactly compensates the increase in the flow strength due to the work hardening there. So it is something like what we have just seen. D sigma by D epsilon is equal to sigma. This is what it is. The moment that condition reaches, that is actually this stage, the necking begins. Thus, the permanent instability is formed at the strain infinitesimally greater than epsilon EU, that is strain at the maximum. And this leads to neck formation. So, we are not telling anything new here, but then this visual pictures of necking, what happens to the strain, okay, before the necking takes place, but then after the plastic deformation commences. So, in between, how the strain distribution occurs within the specimen. That aspect is being brought in this schematic so nicely. So that's why I just wanted to share that. So whatever we have just seen, this table summarizes the whole result. It will be very handy if you just look at them in one table. And we have the fundamental definition of engineering stress, true stress, engineering strain, true strain. And then these relationship just, they appear as it is prior to necking or with some equivalent relations. But after necking, how these relationships is converted, or it has to be looked at, because all these relations are valid till the maximum load, okay, prior to necking. After necking, we can use only these kind of relations, okay, we cannot use the same relation. So that is one advantage. We can just refer this table and then try to understand which are the relations are valid before necking and after necking.